Hello everyone. The title of this video is Using the Intermediate Value Theorem. So in this video, the examples I'm going to do are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 5.3, called Graphs of Polynomial Functions, and I'm under the heading Using the Intermediate Value Theorem. And the examples I'm taking are either examples from the reading, or one of the try it problems from the reading, or one of the exercises at the end of the section related to this particular objective. Okay, so what is, the intermediate value theorem? I'm just going to read it to you from the text here. The intermediate value theorem states that for two numbers a and b in the domain of f, a function f, if a is less than b and f of a is not equal to f of b, then the function f takes on every value between f of a and f of b. Alright, so that sounds a little much there, right? That's a lot. All we're going to use to apply this we're going to apply this to the following concept. Alright, and this is of course for polynomial functions for right now. Okay, polynomial functions. And remember, polynomial functions are continuous and smooth, right, if you remember what those mean from earlier videos. So this is a good picture of how we're going to apply this intermediate value theorem. Do you see how, basically, if the value of a function is negative at one point and positive to the right of it, or positive at one point and negative to the right of that, well, because it's continuous, the graph has to be equal to 0. The graph has to have an x-intercept somewhere in between those 2 points. That's all that means. All right. That's how we're going to apply the intermediate value theorem. So let me show you what I mean here with some examples. So we're asked to use the intermediate value theorem to confirm that the given polynomial has at least one 0 within the given interval. So we're given f of x equals 7x to the fifth minus 9x to the fourth, a polynomial function. And we're asked to confirm that this polynomial has at least one 0, has at least one x-intercept between x equals 1 and x equals 2. So here's what you do. Right, you plug in one end, plug in x equals 1. What's f of 1? Well, that would be 7 times 1 to the fifth minus 9 times 1 to the fourth. This is just 7 minus 9. This is negative 2. Right, so it's negative at x equals 1. Right, so if I were graphing this, the point 1, negative 2 would be on the graph. Right, this point right here would be on the graph of this function called f. Now you check the other end. Right, what about at x equals 2? What's f of 2? Alright, so just replace x with 2, 7 times 2 to the fifth minus 9 times 2 to the fourth. And if you want, these both have 2 to the fourth in common. You can factor that out. Times, and then you'd have 7 times 2 minus 9. 2 to the fourth is 16 times, and then this is 14 minus 9 would be 5. And that's 50 plus 30, that's 80, positive 80. So at x equals 1, the output's negative. At x equals 2, the output's positive, right? If you were graphing, the point, 280 would be on the graph. And the key to this theorem is the fact that the functions are continuous, right? Polynomial functions are continuous. Pardon me. because this intermediate value theorem only applies to continuous pieces of functions, right? You can draw it without lifting your pencil, right? Or continuous everywhere. So if I were drawing the graph's going from here to there continuously. Now I could be doing this, whatever, or just straight there. I don't know. This is a guess. But because it's continuous, the graph has to have some x-intercepts, at least one, right? That's why the words at least one are underlined up here. But by the intermediate value theorem, which I'm going to abbreviate IVT, right? Intermediate value theorem. This function f has at least one zero. At least one zero between x equals 1 and x equals 2. Okay. And we verified that because at x equals 1 you have a negative output, at x equals 2 you have a positive output, and a polynomial function is continuous everywhere, so there's got to be some point between these two that hits the x-axis. There's got to be. All right, I hope that makes sense. And that's all we're doing here. Now if you want to confirm this completely, let's take a look at the actual graph. All right. So I'm going to go to that free online calculator at desmos.com, and I'll enter the function we were given, f of x equals 7x to the 5th minus 9x to the 4th, and then look between x equals 1 and 2. And the nice thing about Desmos is you can actually see the x-intercept. See at 1.286 there's an x-intercept between x equals 1 and x equals 2, right? And remember, at 1, you have 1, negative 2 on the graph. And I'll label it the point 1, negative 2 down here. And then the other point at x equals 2 was 280. 2 comma 80, I can label that point as well. Let's zoom out a bit, quite a bit actually, till we see the point 280. It's way up there. There it is. So, you're seeing from 1, negative 2 to 280, and it's continuous. It's got to cross somewhere, at 1.286, right? It's got to cross at some value between 1 and 2, which it does, right? And it actually only crosses once, right? My little drawing earlier was just hey, it could do this, but it's got to cross at least once between 1 and 2 if you know it's negative on one side, positive on the other, and a continuous function like polynomials are. That's what the intermediate value theorem states in our use. Okay. So let me clear all this stuff out for the next problem. All right, so next example, same thing. Same thing. We're given a function, polynomial function, something we know is continuous, right? Has no breaks in the graph. And we're asked to just verify that there's at least one zero, at least one x-intercept between x equals negative 4 and x equals negative 2. Now, I already know, you can already tell me that x equals negative 3 will work, and that's between, but let's plug these in. What's f of negative 4? So you see it's negative 4 cubed minus 9 times negative 4. Now you can pull out negative 4 if you wish, right? And then you'd have negative 4 squared, which would be 16, then just minus 9. 16 minus 9 is 7 times negative 4. This ends up being negative 28, right? But negative, right? Negative. So if you were graphing this, at x equals negative 4, the output is negative 28. Right? There's that point there on the graph. And then at negative 2, what's the output? If it's positive, then we're guaranteed, because of the continuity of polynomial functions, it's guaranteed that the graph will have to cross the x-axis somewhere between these two. So what's f of negative 2? That'd be negative 2 cubed minus 9 times negative 2. Well, that's negative 8 plus 18, which is positive 10. So, positive. And again, this is a polynomial function, so it's continuous everywhere. So if you were graphing, we'd have to go from this point to this point without lifting our pencil, so the graph's gonna hit the x-axis at some point. Now that happens to be at negative 3. You can check that. Plug in negative 3, you'll get negative 27 plus 27. This is at negative 3, but we don't care about that. All we're trying to show is that, hey, it's negative at negative 4. It's a positive output at negative 2. And because this is a continuous function, by the intermediate value theorem, IVT, this function will have at least 1 0, and it's only going to have 1 0, but we'll have at least 1 0 between x equals negative 4 and x equals negative 2. And that's all we're trying to say. That's all they're asking us to do. Show that it's negative on one end, positive on the other, positive on one end, negative on the other, and the fact that it's a polynomial function, a continuous function, there's got to be an x-intercept between them. Let's verify for sure. Let me show you that negative 3 is the intercept where they're talking about there. F of x equals x cubed minus 9x. And you see, let's go between negative 4 and negative 2, and you can see negative 4 has a negative output, negative 2 input will have a positive output, and I mean, there it is right there. There's the x-intercept between negative 4 and negative 2. It is negative 3. But again, we're not trying to find it, though. We're not trying to actually find the intercept. We're just showing that there's got to be an intercept in between these two x values. Right, by saying it's negative at one of them, positive at the other, and because it's continuous, we gotta draw, take our pencil through the x-axis somewhere in between these two. I hope that makes sense. Okay, and then I just got one more page here. Just a couple more examples. The same stuff, same instructions. Use the intermediate value theorem, and again, that only applies to continuous functions, which, these are polynomial functions, so they're continuous everywhere. All right, so example 3, we're given this degree 5 polynomial function. We're asked to, show that there's an x-intercept between x equals 1 and 2. All right. So what's f of 1? Well, that would just be 1 minus 2. That'd be negative 1. All right, so it's negative. So if I were graphing this thing, you'd have the point 1, negative 1 on the graph. And then what happens at x equals 2? And again, I'll just kind of say out loud here. 2 to the 5th is 32. 2 times 2 is 4. 32 minus 4 is 28. But, all I care about is that it's positive. All right, so 228 would be a point on the graph. And once again, we know it's a polynomial function, so that means it's continuous, right? Its graph should not have any breaks in it or any holes. So there's got to be some x-intercept, right? Now again, it's not going straight there. It might even curve a bit. It might curve a couple times. It might hit the x-axis more than once. But there's at least one x-intercept. There's at least 1 0 in between x equals 1 and 2. Because I know it's negative on one end, positive on the other end. All right. Now that x-intercept would actually be at whatever the 4th root of 2 is. All right. But let's go to a graph and verify this. All right. So once again, clear this stuff out. The function we're given here, f of x equals x to the 5th minus 2x, or just y equals. And then let's go between 1 and 2. And you can see there is an x-intercept clearly between 1 and 2. All right, there's 1, -1. The point 228 should be on this, and the graph is continuous, so it flows from 1, -1 to 228. So it's got to cross the x-axis somewhere, and that's at 1.189, which is, like I said, that should be a 3 decimal approximation of the 4th root of 2, 2 to the 1/4 power. See 1.189, but again, we're not getting into all that. We're not actually asked to find the intercept. We're just asked to show that there's got to be one. All right. Okay. All right. So I just got one more example like this. I'm hoping this seems simple enough. So here another cubic polynomial, which again you should be able to factor and find the zeros of without using the intermediate value theorem. But let's just show that again we got a polynomial function, so it's continuous everywhere. Right. Draw it without lifting your pencil. There's no breaks, no holes, no jumps in the graph. And show that there's an x-intercept. Show that there is a 0 between x equals -1 and x equals +1. Well, wouldn't that just be 0? Again, we're not trying to actually find it, but I hope it's obvious that if x is 0, the output would be 0 here, and 0 is between -1 and 1. But again, that's not what we're trying to do. We're not actually trying to find the zeros. We're just trying to show that there has to be a 0, at least a 1 0 between -1 and +1. So what's f of -1? Well, -1 cubed would be -1 times -2 would be +2, and then minus -1 would be +1, that'd be 3. Positive. All right, so if we were graphing this, the point -1, 3 would be on the graph. And then what happens at +1, right? What's f of +1? Well, that'd be -2 minus 1. That'd be -3, negative, right? A negative output over there. And here you go. And again, the graph is continuous. It's a polynomial function, so it's got to cross somewhere. Again, it might be curvy, it might wave all over the place, but it's got to be continuous, though. It's a polynomial function, so it's got to have at least 1 0. And that 0 actually is at x equals 0. In fact, there's actually more than 1 here. Pretty sure. Yeah. I think there's actually more than 1. So let's see. I think the other ones would be at the square root of 2 over 2 and negative square root of 2 over 2. Well, actually, no. Nope. Don't quote me on that one. Let's take a look. All right, and show that there's that 1 0 between, or at least 1 0 between x equals -1 and +1. All right, so once again, the function we're given, I'll just put y equals this time. Y equals -2 times x cubed minus x. Yeah, okay, just a 1. Right. If that was plus x, there would be a couple, but let's see. But yeah, you see between -1 and +1 on the x-axis, there's a 0 at 0, like I said. Again, you don't have to find it. I wasn't asked to find the 0. I was asked to show that, hey, at -1 you get a positive output. At +1 you get a negative output. It's continuous, so the graph's got to cross the x-axis at least once in between -1 and +1. That's all we were asked to show. All right. That's the intermediate value theorem, the use of the intermediate value theorem for our purposes. All right. All right, so I hope that was all pretty clear, pretty easy. Just a lot of plugging in stuff. All right. And yeah, I hope watching me go over these 4 examples here, helps you in some way if you're ever asked to use the intermediate value theorem to show or confirm that there's at least 1 0 between 2 values on the x-axis on your own. And thank you very much for watching.